This is a photon, or a particle of light. As of the making of this video, it has the fastest known speed in the universe. From the moment it's created, it travels at an astonishing 186,000 miles per second. At this speed, light is so fast that it could circle around the entire Earth roughly 7.5 times in just 1 second. But that's not the only reason why this particle catches the attention of physicists everywhere. The interesting thing about the speed of light is that it seems to be the cosmic speed limit. Even with our most advanced particle accelerators, we can only manage to accelerate matter to just under light speed. The idea of anything traveling faster than this speed is just impossible according to all known laws of physics, but that hasn't stopped some physicists from exploring the possibility that there may be a particle which can give the photon a run for its money. Why is it currently impossible to reach and even exceed the speed of light? Well, a little something called the special theory of relativity answers this. According to special relativity, as an object moves faster, its mass will also increase when measured by a still observer. Now, at everyday speeds, this change in mass isn't really noticeable. But when we start approaching the speed of light, we find that an object requires significantly more and more energy to continue accelerating it because of its ever-increasing mass. In essence, the object's mass seems to approach infinity as it reaches light speed, meaning it would take an infinite amount of energy for the object to reach light speed. So, how do photons manage to do it then? The answer is the four-letter word mentioned earlier: mass. Nothing which has mass is capable of reaching the speed of light. Photons themselves have energy, but according to that famous equation from Einstein, mass and energy can be interchanged for one another, you might wonder. Well, yes, but it's important that you understand that the equation E equals mc squared was derived from this original equation, which also accounts for the fact that a particle's total energy is not just from its mass, but also its momentum, which is related to its motion. Since in the case of light, the mass is zero, the equation can be simplified to energy equals momentum times the speed of light. But doesn't an object need mass to have momentum? You see, light has a feature called wave-particle duality, where it can act like both a wave and a particle. What's interesting about the wave aspect of light is that it allows light to possess momentum without having any mass. To clarify this, let's take a look at the following example. Here we have a rope which is tightly held at both of its ends. If the rope is shaken at one end, a wave can be sent down the rope which can shake the other end. The rope in this case is transferring momentum through its wave motion instead of mass. Similarly, light's ability to act like a wave enables it to use just its motion to possess and even transfer momentum. Photons may not be the only particles in our universe that travel at light speed. Gluons, which are the massless particles that keep atomic nuclei together, could in theory travel at the speed of light. Let's not forget about gravity either. In previous videos, we talked about how gravity could consist of hypothetical particles called gravitons. Now, the mass of the graviton itself is a mystery. However, the thing is, we have confirmed the speed of gravitational waves to be light speed, or c, and gravitational waves themselves are massless. So, is it possible the graviton could be massless and move at light speed? Taking a look at the equation from earlier, if we set the mass to zero, the energy of the graviton is basically the kinetic energy from the graviton's momentum, and the velocity in this case is light speed. So, if gravitons did exist and were massless, they would move at the speed of light from a mathematical standpoint at least. The thing is, the mass of the graviton itself is still under speculation with competing theories going around. One of those theories is a theory of massive gravity, which states that the graviton does indeed have a non-zero mass, which in that case would make gravity propagate at just under light speed. This theory stems from observations that stars within galaxies orbit around the center way faster than they should be able to, just based on the amount of visible matter present, meaning one of two things. Either there is some matter that we cannot see causing this abnormal acceleration, or Einstein's theory of general relativity, which states gravity is caused by an object's distortion of space, does not hold up at very large distances. The first theory is more accepted of the two, with many speculating dark matter being the main culprit for the star's orbiting speed. But if the second theory were true, then general relativity would have to be modified to account for such large distances. This could be done by assigning mass to the graviton. It's important you understand that these theories are still under speculation as physicists continue to study gravity at a subatomic scale. So there's still a lot we don't know yet about the existence and mass of gravitons and their place within our macroscopic understanding of gravity. The only thing left for us to do then is to look at the million-dollar question you're watching the video for. Is there anything out there that could move faster than light? Well, in 1967, the physicist Gerald Feinberg discussed a hypothetical particle called the tachyon, which theoretically moved faster than light. So, how on earth does this even work? Let's take a look at this equation. This equation relates the energy of a particle to its speed as it approaches light speed. Now, let's set the velocity v to be greater than c and solve for mass. The mass of the tachyon is imaginary, and the energy and momentum of the tachyon are decreasing functions of the velocity, meaning tachyons speed up as they lose energy, in contrast to normal matter which gains energy as it speeds up. This means tachyons may not be able to be brought to rest within the frame of an observer who is traveling slower than light speed. So basically, the proper length and lifetime of these tachyons are also imaginary and unobservable. The faster than light speeds that these tachyons travel at also open up interesting paradoxes involving time. Pretend that this axis represents space and this axis represents time. Now pretend we had a tachyon which was generated and then moved through space, and 3 observers, A, B, and C respectively, who witnessed this. Observer A, who is standing still and watching the tachyon, perceives the tachyon traveling forward in time as it propagates through space. Then we have observer B, who is moving in the same direction as the tachyon. Well, for B, the tachyon would only exist in the moment, as it appears to be traveling at a near infinite speed and disappears into infinity in the exact same moment. Now, let's say observer B was traveling a little faster in the same direction as the tachyon. Well, it would then seem like the tachyon is traveling back into the past. This is what observer C's point of view is. So, whose observations are correct in this scenario? The crazy thing is all 3's point of view are equally valid. But how can this be? When it comes to dealing with time at faster than light speeds, you are entering a whole new world of physics that can't just be summed up in a few seconds. In fact, what we just entered will blow your mind as we come face to face with what we perceive as the impossibles of time. After all, how can 3 different observers witness the same event in 3 different ways and all be right? It just doesn't line up with what we're used to. If you want the answers, you're gonna have to subscribe and hit that notification bell then, so you don't miss the next video in our Tachyon series, where we explore time travel paradoxes seen with tachyons. In the meantime, don't forget to stay tuned for more science videos.